All right, all right, all right. With another all right on top for good measure. Howdy, folks. How's everybody doing? We'll go ahead and take down the old epic music. You know, you can have a little too much epic in your life. You're already participating in this epic live stream, so a little too much epic might affect you negatively. It hasn't been tested against COVID-19, but you never know. So I can see your chat over here. So feel free to chat it up. If you see my eyes look this way, I'm looking at your chat. If you see my eyes looking this way, I'm looking straight at you, and I can see right into your heart, and I can see what's in there. I can see what some of you are thinking, and you need to work on that. You need to, I don't know, maybe join a Bible study or something. I'm not sure, but all right. So we're going to talk about some more myths. It's myth time, myth busting time, and I was glad this one came up. This one showed up on Facebook. I was planning to actually bring up the poll that John Oakes originally posted that showed how much controversy there was. So this truly is a controversy because a lot of people got the wrong answer. So hey, that's a good opportunity, right? Something to talk about. But I figured I wouldn't bring it up because I don't want to embarrass anybody. It's an easy mistake to make. It's a mistake that I did make, and I will share that story with you post haste. I literally just ate supper. I ate spaghetti. I ate cooked baby carrots in about 3 minutes. So I set up the stream. I walked into the living room, and I ate my supper. Um, and I don't know about you. I don't know how your day's going, but let me just share quickly a little bit about my day. I've been working on a few videos and some other things, Kalos related stuff, and just nothing went particularly smoothly today. Not a big deal, I'm not complaining, but just nothing went particularly smoothly. And I don't know if you've ever had days like that. And so this is what you're actually witnessing here right now is my attempt at redeeming the day by finishing strong with a video that hopefully you enjoy. So hopefully we can have a good conversation. So here we go. So the questions on the table are: if you change volts, what happens? That's a little joke, what happens? Oh, I'm funny. And then, do motors work different than heat strips? So we're going to start with heat strips, and then resistive loads, resistive type loads, and then we're going to go into motors that are inductive loads. And there is a difference. We'll talk about it, but it's important to understand that we have some additional variables added in. And when a lot of things are taught, they're taught on resistive loads, like a light bulb or a heater or something like that creates light and or heat, not magnetism. When something creates magnetism, we call it an inductive load. And the resistance, that was weird. And the resistance that shows up in an inductive load is called inductive reactance versus just straight resistance. When you take those two and you put them together into a big pot and you mix them up, that's what we call impedance. And it's not a term that we use very often in the trade, but you can measure impedance, which is total ohms or total resistance. Okay, so that's what we're driving at. But one of the things that drives me nuts, I'll lay it right out there. One of the things that drives me crazy is when people say, well, just look at Ohm's Law. Ohm's Law explains it. Not really. I mean, you can know how to do the math of Ohm's Law. You can know Ohm's Law and not actually understand how to apply it in real life. And what is more important? Is it more important to know Ohm's Law, E equals I times R, or is it more important to understand what that means in real life for a technician? And I would argue for a technician, somebody who's out there fixing stuff, that's probably more important to know how that applies in real life. So here we go. We'll start really basic. When the question got asked about what happens if you decrease the voltage on a 5 kilowatt electric heater, what happens to the amperage, I immediately thought of this data tag as well as my mistake, something that I did out in the field that related directly to electric heat strips. So heat strips are fun because heat strips are just resistive heaters, and they actually stay pretty flat on their resistance too, and we'll talk about what that means. But they stay pretty flat. They don't change the resistance too terribly much as they heat up. So you don't see them, drawing one resistance and then drawing a different resistance as they heat up, at least not significantly. So heat strips are a good example of this. And you look at any data tag on any heat strip. Somebody mentioned that I'm looking extra boss baby today. Yeah, my kids my kids watch Boss Baby and just laugh the whole time saying that that's me for many different reasons, not just the way I look, but also my other characteristics, which I'll take. I'll accept that. Anyway, so if you look at this chart here, at 240 volts, it's 9,000 watts. At 230 volts, it's less than that, and we can figure out what that is pretty easy. I actually didn't do the math, but if one of you want to go ahead and multiply 230 times 35.9 and come up with the actual wattage, you can do that for me in chat. It's just 230 times 35.9. And then 208, when you decrease the voltage even lower, the amperage further decreases. So now to see what the wattage is of this heat strip at 208, you take 208 and you multiply that times 32.5, and that will tell you what the wattage is there. But the point is that when you decrease the voltage, you decrease both the amps and the watts. And so the reason why you get confused is because you take Watt's law and you assume that the watts stay fixed, and the watts don't stay fixed. When you decrease the voltage, the watts change. And so you have a moving target. And so the question is, what really stays constant in a resistive load? Well, on the face of it, it would seem like the resistance stays constant. And in this case, with a heat strip, the resistance is what stays pretty constant. And so in order to really calculate what's going to happen when you change the voltage, you have to start with Ohm's law. So you have to start by multiplying your resistance. It's E, voltage equals amps times ohms. So you have to start by with your resistance and then do the math, and we'll do that as we go to the next slide. I keep wanting to get ahead of myself. So anyway, but let me tell you the story about my mistake, and I've shared this on the podcast before, but I don't think I have in a video. This is a heat strip restring kit that's right behind my head here. Let me remove my fat head so that way you can see it. This is a heat strip restring kit, and we used to carry these on our trucks when I was a laddie. A young technician. This probably would have been 2001, something like that. And I was out. It was a very cold winter in Florida, which does happen on occasion. And I was out working on a package unit. It was a ground level package unit, and I had one of these restring kits, and I was trying to figure it out. I'd never actually done it before, and so I was trying to figure it out, and the insulators and all that. Well, as it got towards the end, and I was trying to make my termination, I kind of bent it at a weird angle, and I broke off a piece of the restring kit. And I thought, well, I'll just figure it out. I'll remake a connection. I'll just cut that piece off, and I'll make a new connection. I thought, well, cutting a piece off of this restring kit certainly isn't going to hurt anything. It just may make a little less heat. It made sense to me. Cut a little bit of the heat strip off, it'll make less heat. It'll draw less amperage, right? That seemed to make sense to me. Well, that's not what happened. By cutting a little bit off of it, what you're doing is you're reducing the resistance. By reducing the resistance, you increase the current if the voltage stays fixed. So pretty simple, right? That is really the ramifications of Ohm's law, and we'll get more into that. But if you reduce resistance, you increase amperage. If you increase resistance, you decrease amperage. That is absolutely always true, and that is absolutely how it works. The challenge just is that in many cases, you can't ohm it out and then apply current through it and have it continue to still behave in the same way. And there's several different reasons why that is. Okay, so let's go ahead and end the myth, though. We'll just get that out of the way before we go too long in this video and just say, myth busted. When you decrease voltage on a resistive load, absolutely what happens is you decrease wattage and you decrease amperage. Decrease voltage, you decrease wattage, and you decrease amperage. That's Watt's law and Ohm's law. Because the thing in that equation that's staying the same is the resistance, and then the voltage is going to be fixed. I mean, your input voltage isn't going to fluctuate, at least it shouldn't. And so that's where you start. You start with those two variables, and then you build your way up. See if we have any questions so far. All right, there we go. Joe says, I must have cut more than just a little bit. Joe, I don't remember, okay? It was years ago, and now you're going to judge my story. It's a true story. I'm not going to be ashamed of my story. And yes, it drew high amps, and the thing started glowing, okay? Maybe I cut a lot off. It's possible. I'm not the brightest boy from Groveland who was ever born, I'm sure. All right, so let's take a look here at at something interesting. So we take a heat strip, and we're just going to further prove this. We take a heat strip. I put it on a DC regulated power supply, because AC or DC, it makes no difference in how a resistive load functions, because it doesn't make any use of that. By the time you do the true RMS, so you actually look at true root mean square, what that actually is for alternating current, and you compare that to direct current, it's going to function the same, 24 volts AC, true RMS, as it is 24 volts DC in a resistive load. So if we drop the current all the way, like we did here, to 24 volts, this particular heat strip, and I don't even know what this one is, it's probably a 5K or whatever, it's all the way down at 1.5 amps. So we've proven at this point, when you drop voltage on a heat strip, you decrease the amperage. That's all I was trying to establish there. Not trying to get too complicated. All right, so one thing, again, that people always say is, it's just Ohm's Law. Just memorize Ohm's Law. That's all you got to do, memorize Ohm's Law. I would suggest that you stop saying Ohm's Law unless you know specifically what you're solving for. I mean, this, you've got the V over I times R. That's one way of doing it. V divided by I equals R. So you solve for whatever, you cover one, and that's the one you're solving for. So if I'm trying to cover it, of course you can't see me covering it here with my finger. Let's see if I can reach up here and cover it. No, my finger doesn't quite make it here. But if I cover for R, then I divide volts times amps, and that equals resistance, so on and so forth, right? And that's the basic philosophy. If we increase voltage, voltage is the force, then we're going to get more amperage if everything else stays the same. If we increase ohms, that's the resistance against the force, and we don't change anything else, then our amperage is going to be lower. If we increase resistance, amperage will be lower. Decrease resistance, amperage will be higher. Okay? The reason why so many people get confused with that increase, decrease of resistance thing is that in our minds, I think we imagine that if there is more physical resistance, we're thinking about motors here, there's more physical resistance to the motion of a motor shaft or to something moving, that physical resistance equals electrical resistance, and it does not. The more physical resistance you have against a motor moving, so you have a locked compressor, more physical resistance, the less electrical resistance you have in impedance. And we'll get into why that is. It's a whole inductive reactance thing. So on one hand, you have to know what you're solving for if the others stay the same. But in real life, when you change one, you also generally change the others, which is why this kind of gets complicated. When we do it really basic math, using a direct current power supply, so we don't have to factor in anything on the alternating current side. We don't have to think about power factor. And then when we're using resistive loads, that makes the math a lot easier. But even then, it gets a little weird. And I have a article about this that I shared a while ago, that Ohm's Law ain't simple in real life, even with something as simple as a light bulb. So if you measure the resistance across a light bulb, you measure the ohms across the light bulb, you would think that light bulb would actually have a lot more resistance than it does. But the reality is that once it actually starts to heat up, a lot more current than it does. Once that light bulb starts to heat up, the resistance begins to increase. And that is a property of many metals, but tungsten is one of the metals that's in a filament on a light bulb. So even with something as simple as a light bulb, using a direct current power supply, even then, you can't just work Ohm's Law, because you could only do it if the light bulb was already hot. And how are you going to measure the ohms on a light bulb that's already lit? And the answer is, the way you measure the ohms is by working backwards, by taking the voltage and the amps, and then you calculate the ohms. So again, if you want to do the math on this, you can, but generally it ends up being about 10 times, meaning that it's about 10 times more real resistance shows up once you heat up that bulb than when the bulb is cold. So even with what we would probably consider the most simple electrical circuit in the world, one that we've got right here with a light bulb and a DC power supply, even then, if you look carefully at the box, it does line up exactly with the box using the DC regulated power supply. But if you try to work Ohm's Law, it doesn't make sense, because you think to yourself, well, I measured the ohms and it's the math isn't working. Well, the math's not broken. It's just that the only way to do the math is in real life. Eric Melley says, oh, good, I was getting worried. You know what, Eric? Oh, man. All right, so next thing is inductive loads are really tricky. So here's one. I pulled up this particular compressor in the Copeland mobile app, and I looked at the winding resistances. So take a look at the start and run winding resistances on this motor. And if you take a look at that run winding resistance, because run is the winding in single phase that's connected across the line, so between L1 and L2, your start winding is connected in between one leg and a capacitor, so the capacitor acts as a limiter. But if you take that 0.46 and you work Ohm's Law with that at a 240 volt power supply, that would equal something like, I think it would be 580. Yeah, that would be about 580 amps that compressor would draw if it was just based on the resistance of that winding. In fact, a lot of meters, if you were to connect to this compressor with a lot of meters, it would say that it was shorted, like it would just go to zero, dead short across the windings at 0.46 ohms. And this is a huge mistake a lot of new technicians make. They measure across the windings and they say, oh, that resistance seems too low to me, the compressor's shorted. Well, no. Check it against Copeland mobile app or whatever compressor manufacturer data you've got, and you'll find that it's probably just fine. Because the reason why that compressor doesn't draw super high amps like that is because as that motor starts to run, as that motor starts to speed up, get up to speed, close to synchronous speed. Sorry, I got a bad cord there. As it starts to get close to synchronous speed, inductive reactance shows up. And inductive reactance is that magnetic resistance. It's just a simple way of thinking it. That's opposing the force, and it only happens, or opposing the current, and it only happens once that motor is up to speed, which is why as that motor is speeding up, the current is high until that motor gets up to speed and the true impedance shows up. Again, that's the resistance, the basic electrical resistance of the windings themselves, plus that inductive reactance all mixed together, and that's what drives down your current. So what that means is that if we were to just do Ohm's Law on a compressor, we would think that the thing would draw crazy high amps. And of course it does for that very first millisecond, that very first cycle. There is high current drawn. Inductive reactance is the impedance, or the resistance that keeps the current down once that motor gets running. More slip equals less inductive reactance. So the more a motor slips, the more physical mechanical resistance there is against the operation of that motor, the higher the current's going to be because you have less resistance. Remember, less resistance equals more current. Now let's talk about what happens with voltage, okay? Because I've done this. I wish I had the video that I could show you for this purpose, but I've got an adjustable auto transformer. I'm trying to remember what the name. There's a technical name for that. Variac. I've got a Variac in the office, and so I can drive down the voltage to a motor. And I've got a little blower, 120 volt Variac. I plug it in, and I drive the voltage down. And so what happens on a motor when you decrease the voltage? The answer is it varies by the motor and the load that the motor's under. But at least in my lab and with the motor that I've got, and it's a regular PSC blower motor, it's got a capacitor on it, all that. When you drive the voltage down, the current also goes down. It just doesn't go down as fast as the voltage, meaning that you have two things going on at once when you drive the voltage down on a motor. On one hand, you're decreasing the applied voltage so that motor starts to slip. As that motor starts to slip, it starts to use the voltage applied to it, the potential applied to it, less efficiently. More of it is going to heat. So what really happens inside of a motor when you apply inappropriate voltage, when you apply voltage that's too low to the motor, then that motor starts to run hotter in terms of, it may not actually run hotter than it was before, but there will be more percentage of waste towards heat. So from a very practical standpoint, the motor will run inefficiently. If you apply too low a voltage, the motor will run inefficiently. Okay, so that's one critical thing. And eventually the motor will stall. So eventually if you drop the voltage low enough, the motor will stall. But by the time it gets to the point that it does stall, your voltage, at least in my testing, and it depends on the load the motor is under, but your voltage is going to be so low that even then your current will tend to be on the low side. And again, this is a curve. This isn't linear. You would have to, every different motor would be slightly different, and you would have to test them independently in order to know what the result would be. So the answer to that question is, what happens when you reduce the voltage on an inductive load on a motor? In many cases, the amperage still goes down. But it's not linear like that, because as you're decreasing the voltage, you're also decreasing the inductive reactance, which in turn means changing the voltage on a motor, you're dialing the voltage back and you're dialing the resistance back at the same time. So inefficient, they don't run well, they're not doing the job they're supposed to do. That's from a very practical standpoint. So the answer is don't apply voltage that's lower than a motor's designed for. Now, I was trying to find it, but certain manufacturers will also give charts to show on a 208, 230, 208, 240 appliance, like a condenser, how it will produce less overall capacity when you run it on 208 than you do on 240. And the amperage will actually be slightly lower. So you'll have lower capacity, and you'll also have lower current. Again, on some of the charts that I've looked at, and I looked for 15 minutes, I couldn't find one, so I just let it be. But I've definitely seen that in the past. So if anybody wants to find that. All right, let's see. We got anything else? All right, yeah. Conclusion is know what stays constant or the variables. And the reality is that when you're doing electrical math, very rarely do you only change one thing. And the mistake that a lot of people make when they think that, I'll end here because this is a common one, when they think that when you decrease your voltage, your current goes up. The reason they think that is because they've seen things like an 120 volt motor drawing double the current of a 240 volt motor. But what they're missing is that motor, say it's a 3/4 horsepower motor, and you have them sitting next to each other. One's 240, one is 120, and you know the one that's 120 draws double the current, so you just assume lower voltage equals higher amperage. Well, no, it has to be double the amperage in order to still do the work. So in order to produce the horsepower, in order to produce the wattage of output, you have to design the motor differently in order to come up with that result. Same thing is also true if you do. I mean, it's a good example of this is like a motor that's an ECM motor that's on a variable frequency drive versus a motor that isn't a PSC motor. When you take a PSC motor and you dial back the voltage, what happens? The motor starts to slip, it starts to run inefficiently, so on and so forth. You do the same thing, you dial back the input voltage to a variable frequency drive, and what does the variable frequency drive do? Well, it can control its output, so it has a wider range of acceptability, and that will, you back off the voltage slightly heading into a variable frequency drive or into an ECM, you definitely will see an increase in current because you have something that's actively changing the wattage, actively impacting the output of the motor. And so it really depends, what type of device are you working on, what the result will be. But assuming, for example, with a heat strip, that because it's a 5,000 watt heat strip, that just changing the voltage is going to now make the amperage go up in order to keep the wattage the same. That's not how it works. There has to be something actively doing that in order to make that happen. All right, so that is that. We're going to open up our chat window here quickly. I do want to encourage you, if you have not yet subscribed to the HVAC School channel, please do so. Click the red subscribe button and then hit the bell, hit the bell to be notified when we go live. That would be much appreciated, and then that way you'll actually know when these things go live. Because every time I do one of these, afterwards people say, I wish I would have known when you went live. Well, there you go. Hit subscribe, hit the bell, and there you have it. So we're going to go ahead and bring up chat now so I can see what y'all are yammering on about. What happens with the electrical during a power surge? How does that affect the motor? So that would be an increase in voltage. When you have an increase in voltage, you're going to have a spike in current as well. But generally speaking, when you talk about a power surge like a lightning strike or from something with the distribution power supply, that's usually an instantaneous surge, and those are very quick. And the only way to prevent those is to have some sort of all of a sudden metal oxide varistor type system, some sort of surge protection system in order to help grab that current and shunt some of it to ground. If that goes through the motor, if you have a surge, high voltage that goes through the motor, yeah, it absolutely can damage the motor because the current is higher. And we all know that. You increase voltage, current goes up. Decrease voltage, current goes down. That's the reason why it damages things. It's current that makes things hot. That's the movement of the electrons and how many are moving. Surge puts more wear on the device for the duration of the surge, correct. Regina says, are you working in the Virginia area? No, we are not. Let's see. Horsepower equals watts divided by 746. Right, there's 746 watts per horsepower. That's all it is. It's just and in the case of what we're doing, we're generally thinking of it in terms of the work that it produces. Are there any power surge protectors for blower motors? I've already burned out on me suspecting a power surge. Yeah, Zebra makes one, and that's specifically designed for ECM motors. Eric says ICM makes one, but you can get them that work on anything. Good quality one will work on anything. My favorite device out there is the ICM 493 because it also deals with low voltage conditions, high voltage conditions, and surges all in one box. It's not cheap though. Most people that ask these questions don't understand what they are looking for. A simple answer to a very complicated question. It's almost never as simple as it seems. That's what Corey says. And yeah, that is true. And in many cases, we don't really need that full answer. In many cases, we don't need to do the math. That's, again, when I'm talking about technicians, we're not engineers. We're not designing new motors. Nothing wrong with learning how to design a motor and how to do the math. I know some people who like to do that stuff, and I do sometimes as well, and it's a good nerdy endeavor. But out in the field, you do need to know what will happen. Or at least that it is a bad idea to have under voltage or over voltage for various reasons. And it may not be as big of a deal if you are feeding that input voltage into something like a variable frequency drive. Or it may be a big problem, like we see with certain models where if you have over voltage into the variable frequency drive, it causes the actual entire board to fail. So again, it's all about knowing your equipment and knowing what the results are. But like I talked about in my initial story, my misunderstanding of a heat strip resulted in me cutting a piece off and thinking that would decrease the wattage or decrease the amperage, and it didn't. It increased it. With no motor specs and an unreadable capacitor, is there any way to find the correct size cap? And the answer to that is, here's what I would do in a case like that. I would guess at it. I would put one in, and then I would use a power quality meter like the Redfish or the new Field Piece and look at my power factor and just kind of keep adjusting until I get to 1 or as close to 1 as I can. That's the simple answer, because in a lot of cases, and it also depends on your applied voltage, the manufacturer is basing their capacitor sizing on 230 volts. So if you have more than that, your size may actually be off. And so starting to measure power factor is actually an interesting thing, and you'll find in some cases that that sizing your capacitor based on power factor, you may actually run a little better. Again, it's not. It is a confusing thing because that's not the only thing a capacitor is doing is power factor correction. But if you get your power factor right on the compressor or whatever motor you're on, you're going to be in good shape. Chuck says, how does that find my cap size? Well, I don't know if you heard what I just said, but I said try it. So put one in. You're not going to know beforehand. It's not like you're going to be able to know for sure what the right size is. But if you roll up on a 3-ton system and it's got a bad capacitor on the compressor and you can't read it, and you can't read the compressor to find the specs to find, and you can't read the data tag, then put in a 35 microfarad capacitor and then check your power factor. Check your amperage, check your power factor. And if your power factor is, 0.98, 0.99, you're pretty darn close to what it's supposed to be for that. If you don't know how to check power factor, that's fine. Most people don't, but you have to have a meter that does that. But that's the way you would do it. There's not like an easy way for you to. It's not like you can just go measure the resistance on the motor and know what your power factor or what capacitor you should put on it. You just gotta try it. And I would feel totally comfortable doing that. I have a Redfish meter in my bag, and if I didn't have that data, I would look at the motor itself, look for the model number. You can go back to the manufacturer and find it based on the motor. But if you don't have that, then that's all you can do. All right. Well, thank you so much. Thank you all so much for watching, and I'm going to probably do another one in the next couple days. Appreciate you, and we'll see you on the next HVAC School Myth Busters podcast video thing.